All right. So last time we spent most of the day just trying to get used to the idea of a magnetic field. So they're really different than electric fields. So with an electric field, again, you just got F is the charge times E. So basically the force is either in the same direction as the electric field or opposite of it. So that means charged particles sort of follow the electric field. All right? But for magnetic fields, it's completely different and it's weird. So for magnetic fields, you've got F is Q times V cross B. So the force is always perpendicular to the magnetic field, and it's also perpendicular to whatever the velocity of the particle is. And we said what that means, and if you want to try to imagine it, is usually what happens is that a charged particle moves in circles around the magnetic field. So if I've got a magnetic field going this way and I have a charge that's moving perpendicular, then it'll wind up just kind of going in a circle around it. Okay. So that was kind of the big thing we talked about last time. And then we looked at the homework a little bit. And of course, my memory is always horrible, so I have no idea what we looked at. I'm guessing we probably did the 20.08 since it's a difficulty 3. There is a difficulty 5 down there. Yeah, we didn't do that one. But it's kind of far down. Let's do a couple of these 2s in the middle first, and then we'll do that one. So did we do any of the 19, 14, or 26, as far as you know? So didn't, okay. Let's look at 19 for now. Actually, so you've got a beam of protons accelerated through a potential difference of that many kilovolts and enters a uniform magnetic field traveling perpendicular to the field. What magnitude of field is needed to bend these protons in a circular arc of diameter that? Okay. So we kind of talked about this sort of thing yesterday, or on Friday. And basically, all we need to do is we need to find what's the velocity of the protons as they get into the field. And then we just set the magnetic field and the magnetic force equal to centripetal force, and then we can solve for the magnetic field. Okay. So first of all, let's do this potential difference thing. So 0.745, so that's 745 volts, right? What does a volt mean? Remind me. What is potential difference? So electric field is kind of like force, right? It's force per unit of charge. Potential difference is kind of like, and what's the other big thing in physics? There's forces, and then there's the other thing that's conserved that we love. That's really too vague, isn't it? Yeah. Yeah. So, I mean, your two big concepts in physics are force and energy, right? I mean, everything kind of Yeah. So that's what potential difference is. It's potential energy per unit of charge. So V is, see if I can get my pen to write. V is potential energy per unit of charge. So the potential energy difference is, well, 740. It says a beam of protons, but we're looking really one proton at a time. So the charge of a proton is 1.6 times 10 to the minus 19th, and then times V, which is 745. Get my pen to write. All right, so grab my calculator right quick. $745 times 1.6 is 1. So 1.992, and that's going to be 10 to the minus 16th. So that's my change in potential energy as I accelerated at the beginning, right? What I really want to know, though, is the velocity as it enters the field, right? So whatever the change in potential has got to be the same as the change in kinetic, right? So what's the formula for kinetic energy? So kinetic energy is 1/2 mv squared. Yeah. I can get my pen to write. There we go. So, okay, on one hand, it has to be the same as the change in potential. On the other, it's 1/2 mv squared. So that's 1/2. The mass of a proton is 1.67 times 10 to the minus 27th v squared. So we can get what V is. So V is square root of 2 times 1.92 times 10 to the minus 16 over 1.67 times 10 to the minus 27. And that square root is a, whoops, big square root. All right. So, all right. So times 2 divided by 1.67. And this is going to be, that minus 27 will become plus 27, so this is times 10 to the 11th. Let me actually do that. Times 11, 10 to the x, and then square root. So 377,828. No, my pen won't write. There we go. Now that it writes, I forgot what I had. 377.8 times 10 to the 5th. All right, so that's our V, right? And once we know that, well, to get the, so let's go back to the problem. So all we've done so far is we've said, hey, if you have a proton, you accelerate through that potential difference. How fast is it going when it gets to the end? Now it's going to enter a magnetic field, and we want a circular arc of that diameter, right? So to get the field, well, on one hand, we know that the field is making centripetal force, which is mv squared over r. On the other hand, we know that, well, magnetic field, you're going to have Q times V times B. Right? And then you have sine of theta, but if it's moving in a circle, then the V is always perpendicular, so it's 1. Okay, so we know M, it's 1.67 well, let me go ahead and get V by itself because that's what we want. So B would be mV over RQ. So M is 1.67 10 to the minus 27th. V we just got was 3.778 times 10 to the 5th. R is half of the diameter, which is wow, I can't even do that in my head this morning. 1.79 divided by 2 is 0.895. Okay. It is too early in the morning. And then Q is 1.6 times 10 to the minus 19. All right. So that guy is in the denominator, so 1 over x, and times 1.67 times 3.778 divided by 1.6. Is that, I'm going to have 19 and 27, that would be 8 plus 5 is -3. So I think it's that times 10 to the minus 3. So 4.41 times 10 to the minus 3. Let's try it. All right. Okay, if we had electrons instead of protons, I'm not going to rework it because we actually would have to rework quite a bit. But the only thing that's going to change, I mean, there's two things that's going to change. The mass of an electron is, I think it's 9.11 times 10 to the minus 31, if I remember right. We can ask almighty Google here in a second. The mass for an electron, I think, is 9.11 times 10 to the minus 31. So that'll change right here in our formula for B. But it'll also change one more thing because it'll change V, right? Because to get V, we said it was 1/2 mv squared, so we'll have to change that there. But otherwise, the problem's exactly the same as part A. So let's ask Google just to double check what the mass of an electron is. But I'm pretty sure that's right. Mass of an electron. I don't want a discussion on it. I want to know what it's equal to. Yeah, here we are. So yeah, mass is 9.11 times 10 to the minus 31. Right there. So, cool. All right. So that was 19. Let's look at 14. And then well, depending on how this one goes, we may jump down to the 5 or we may do the next one first. So now for particle, helium nucleus, so 2 protons, 2 neutrons, actually.